So the kinetic energy still is defined as 1/2 mv squared. And basically, here you see again your textbook is showing kinetic energy with T. I would go with K instead of T to stay consistent with our previous lectures. And so clearly you see again here is the derivation of work energy formula. So nothing is new. And again, you clearly see that the work energy principle holds for a rigid body as well, because a rigid body is a system of particles. So here it says that the work done by external and internal forces. Okay, so pay attention that it is all of them and couples. As a rigid body moves between two positions is equal to change its in kinetic energy. So here E might be misleading. Not necessarily all of the work done by internal forces is equal to 0. Okay, so we have to pay attention. This is all of it. So if you want, I can reformulate this, but we're going to use a new version as we go to all solving problems. We're going to use a new format for this formula. But if you want, I can take this E off so that it's not misleading, that it's only external forces. Now, the problem is when you have a rigid body, so this is for a system of particles, okay? But when you have a rigid body only, a rigid body, internal forces, their work always cancel out. If you have a system of rigid bodies, that's a separate story, okay? So if you combine several rigid bodies into a single free body diagram, then the forces exchange between them, the internal forces of that system. Some of the work done by them might not necessarily cancel out. Okay, so we have to pay attention. But if it's just a single rigid body, and we consider a single rigid body as a system of particles, then yes, the internal forces between the particles inside the rigid body are only basically gravitational attraction, and they definitely cancel out. Okay, so we have to pay attention, but the principle of work energy still holds, still exists, and we can use it. Now, one of the big changes when we want to do it for a rigid body compared to a particle is kinetic energy does not come only from a linear velocity v. In other words, if you have an object that basically has linear velocity, and let's say here this linear velocity, you know, different points have different linear velocities. So this v that we show here is v of the centroid. And then this object also rotates, then the kinetic energy is two terms: the rotational kinetic energy and the translational kinetic energy. For a particle, since there is no rotation, the second term is basically gone. But for a rigid body, not necessarily. Okay, so the first big thing, so we still say that some of the work done on the rigid body between two positions is equal to change in its kinetic energy. No difference. And here I use W for showing work, not U, and I use K for kinetic energy. But as I said, K, kinetic energy, is basically it includes two terms. One is the translational kinetic energy, which is 1/2 mass of the object times velocity at the centroid squared, plus 1/2 I about the centroid times omega squared. If you see, these two terms are similar, right? There is a 1/2 in each. There is an inertia in each. This is translational inertia. This is rotational inertia, and then magnitude of velocity squared. So this is total kinetic energy for a rigid body. That's the first big difference that we have here, and you can see. Now, this is general, right? So now let's just see in special cases what happens to this formula. And let me make this a little smaller so that we have room for other stuff. So let's make this a little bit smaller. There we go. So now if you have translation only, so the rigid body does have pure translation, okay? When it is pure translation, then K is, of course, what? Only 1/2 m v squared. And here, when the object has pure translation, the velocity of the centroid is the same as velocity at any point else on the rigid body. That's the condition for translation. So here, this can be written like this, and this reference point does not matter because it can be any arbitrary point when you do pure translation. Now, if you do pure rotation, there are two scenarios. Either you do this pure rotation about the centroid, so the rigid body is rotating about its centroid, like what? Like gears, right? So this is when your rigid body here has just pure translation, like this object that is just doing pure translation. Here is when the rigid body is rotating about its centroid, like, as I said, a gear. Then, of course, K is what? 1/2 I about the centroid times omega squared. Why? Because V of the centroid is 0, right? The centroid is the fixed point. But sometimes the centroid is not the fixed point. So about an off-center point. So sometimes your rigid body is rotating from about an off-center point. So you have an object like this, like a cam. And what is cam, I can tell you, but you're rotating about an off-center point. In this case, if I call the fixed point point O, clearly the centroid is not there, so the centroid does have a velocity, which is not 0. So I should include both of the terms, 1/2 m v centroid squared plus 1/2 I about the centroid omega squared, but you can combine them together and just write it as K equals, so let me write it for you. It is 1/2 m v of centroid squared plus 1/2 I of centroid omega squared. Now my question for you is, how much is V of centroid if this object is rotating with angular velocity omega and the distance between centroid and the fixed point is d? Okay, this distance here is d. What is velocity of the centroid? Magnitude of it. You are right, it is what? D times omega, because the centroid is rotating about the fixed point, correct? V equals R omega. So if you plug it in, this guy is going to be d squared omega squared. And then, correct? And then if you factor out 1/2 omega squared, you would get K is 1/2 of md squared plus I about the centroid. Correct? And what is this guy here? I about the centroid plus mass times distance squared. According to parallel axis theorem, this guy is, you're right, I about the fixed point times omega squared. So if you're rotating about a fixed point which is off center, Since the object has pure rotation about that point, you can say that the only kinetic energy I have is a rotational kinetic energy, but the reference for calculating the moment of inertia is what? Also that fixed point, not the centroid. So you can do that, and this is what I mentioned here in the lecture. So you can see all different cases, right? There we go. By the way, I mentioned cam, I guess, several times in my lectures. If you don't know what a cam is, let me just show you very fast. Because I really feel bad when I mention something and I'm not 100% sure if you know it or not. So if you have been dealing with engines or cars, you probably know cam and camshaft. But if not, I would like you to see that. So let me get a good picture. This might be a good picture, but no, too small. So this is like a camshaft of the car, but I want to see if I can show you an animation of it. Cam animation in the engine. Maybe this one. Carpet valve engine. No, that's not the right one. Camshaft engine. So this is doing definitions on this channel. So let's look at an animation, if I can find a good animation. That would be camshaft work, maybe this one. Yes. So if you look here, these are the pistons inside the cylinders, and here it does not show the cylinders. And these are the valves that basically allow the mixture of air and fuel to come in, and then basically exhaust mixture, the one that is burnt, to get out. And in order for these valves to open and close, there is this rotary object that looks kind of like an almond. Okay, and this object is clearly rotating about an off-center point, and this shaft here is called camshaft, which is rotated by the crankshaft using the timing belt. And so as this cam rotates, since different points on the cam have different distance from the center, sometimes the excessive distance makes the valve go down, and when the distance is shorter, it makes the valve go back up. Okay, so this is the mechanism, and you can see it better here probably. Let's see. Here, yeah. Okay, so let's look here as it works. Okay, so these are the cams, these are the valves. You see, it is rotating about a point here, an off-center point, and it allows for the valves to basically open and close. Okay, so cams are an example of that. Just wanted you to know this thing that is an important mechanism in the cars. Okay, good. So we learned about how to formulate kinetic energy in a rigid body. The other thing we need to talk about is work and potential energy. So work was defined as integral of force dot displacement. Now, when you have a rigid body, the force can be applied at different locations of the rigid body, right? Because a force is only applied at one point in a rigid body, correct? So, and you know, different points on the rigid body, they have different displacements. So when this force here is applied to this point P, when I want to calculate the work done by this force between position 1 and position 2, when I say F dot dr, this dr belongs to which point? Of course, the point at which the force is applied. Okay? So it's not the displacement of centroid again. It's the displacement of the point at which the force is applied. So, in other words, if I want to show you with a simple picture here, so this is a rigid body, this is called point P, this is called point Q, let's say this is called F2, and this is called F1, and let's say this rigid body is rotating about a point here, for example, or no, it's arbitrary motion. So clearly we know that this point has a different displacement in a very small time compared to this point. Different directions, different magnitudes. So when we calculate the work, we say work is the integral from position 1 to position 2 of force F1 dot dr of P plus from R1 to R2 of force F2 dot dr of Q. And then if there was F3 that was applied to point C, you do F3 dot drc and so on and so forth. So each force is dot producted with the displacement of the point at which it is applied. Okay, that's the only difference. Not all of them are applied to the centroid. The only one that typically is applied to the centroid is weight, or always applied. Sometimes if you are pivoting the centroid, then you might have two more reactions, although then if you pivot it, centroid does not move, so those forces will do nothing. Okay, and then we come to the conservative forces and the work they do and the way that we define potential energy. So the change in potential energy was defined as negative of the work done by conservative forces. And the same definition applies here. No difference. You can see that. So then you can say that the work of the gravity, therefore with the negative sign, is change in the potential energy due to gravity, and then the same thing applies for spring. So no change. If there is a linear spring, still the potential energy at any point is 1/2 ks squared, where s is the elongation. So no difference. Okay, so let me write it here. Again, negative of the work done by conservative forces is equal to change in potential energy, and I use P instead of V. And so the potential energy due to gravity, the change in potential energy due to gravity is mg, or W, times delta y, the same formula, where here delta y of which point? Delta y of the centroid, because gravity is applied at the centroid. The change in potential energy in a spring is equal to k over 2 times s2 squared minus s1 squared. Okay, so this is for linear spring. And then for a, there is now a new thing called a rotational spring, or torsional, what we call it, spring. So for a torsional spring, it is equal to k theta, or kt, over 2 times theta 2 squared, or delta theta to delta theta squared. Okay, if you want, I can write it at one single point instead of the delta of it. So if you want to write it as a single point, we can write it like this. So this is the potential energy defined for rigid bodies, and this is for a linear spring that we had in the past. If linear spring is attached to any rigid body, this is for gravity. And this is for torsional spring potential energy. Now, what is torsional spring? Let's talk about that. So, torsional spring is a spring that the moment of which is equal to negative of the constant of the spring times the angle through which it has rotated. Remember, the force of a linear spring is negative k of the spring, the spring constant, times the displacement. So here, if we assume that the torsional spring is not twisted when theta is equal to 0, then the moment, the couple that it applies when you twist it for an angle theta is going to be negative k times theta. And to distinguish between k of a linear spring and k of a torsional spring, I use k sub t to tell you that this is the torsional constant, not the linear spring constant, because k and kt are two different things. Okay, so this k, if you look at the unit for that, the unit is what? Because for a linear spring, let me show you, for a linear spring, the force is equal to negative k times delta s, and for a torsional spring, the couple, the moment that it creates and resists twisting, is negative k sub t times delta theta. So clearly, if you see, the units are different. Here, the unit of the linear spring constant is equal to what? So the unit for this is Newton per meter, right? Because that's Newton that meter. But what is the unit for this one? This guy is Newton meter by itself, and this is radian. So it's Newton meter basically, because radian is literally has no dimension, right? You know, radian has no dimension. So this is Newton meter per radian, this is Newton meter. So these are two different things. Now, you might wonder, what is a torsional spring? Again, you might or might not have seen torsional. I'm sure you have. I'm sure you have all seen it, just maybe not recognize it with that name, but I guess everybody has seen them in their toys and in so many different applications, right? So these torsional springs are the ones that you see in many of paper clips, in many of the toys, in even some older clocks and so many other things, okay? Where if you twist it through some angle, then it would like to apply a negative backward couple and go back to original angle, Okay, so these guys you see a lot in some mechanisms for the door stops and so on. So these torsional springs are quite common in so many different applications. Just wanted you to know how they act. Okay, and again, this linear behavior is assuming that the angle through which you are twisting is not super big. Okay, then they might be shown some nonlinear behaviors. So this is the potential energy stored in a torsional spring. This is the potential energy stored in a linear spring. This is the potential energy stored in any object that is lifted. Okay, so these are what we have here. The change in potential energy is negative of the work done by conservative forces, no difference. Everything is the same. Kinetic energy is a little different. Work, as I said, is force times displacement of the point at which it is applied. Now, one new other thing we have about work. So the work done by the force is F dot dP. Now, sometimes not only you have forces applied to the object, you also have what? You also have a couple or a moment like M that is applied to the object. How do you determine the work done by this couple? So the work done by the couple is equal to, instead of integral of F dot dr, it is integral of M d theta. Okay, from theta 1 to theta 2. So this is the work done by a moment or couple on the rigid body. Okay, so if anybody asks you, how would you calculate the work done by a moment when the object has been rotated through angle from theta 1 to theta 2, this is how you do it. And again, I have mentioned that as well in the lecture that you should be able to see it. Let me show you where. So this is the the potential energy for torsional spring that I mentioned, and here. This is the work done by a moment or couple. Okay, so I also mentioned that for you here. The principle of work energy is the same. You can write it as K2 total mechanical energy 2 minus total mechanical energy 1 is work done by non-conservatives, and if non-conservatives are 0, then you say that the total mechanical energy, and remember mechanical energy was sum of potential and kinetic, that is equal to, in position 1 is equal to in position 2. In other words, it's conserved, right? So here, this is this one. I just want to make sure that you know and you have access to anything that you want to have and you need. So this is this one, this one, this one, and now again I write them for you here. That you can also say the principle of work energy is, one way to write it is this one. This is the original form. The other way to write it is, you say work done by only non-conservatives is equal to K2 plus P2 minus K1 plus P1. And again, if this guy is 0, then you have the mechanical energy to be conserved, right? So if this is 0, for some reason my pen does not act properly. So if this is 0, oh gosh, that's really hard to do. Let's see if I can. this is 0, then I can say that mechanical energy 2 is equal to mechanical energy 1, and it's conserved. By the way, again, I'm saying that in your textbook, let me write it somewhere for you. So in your textbook, is using T for kinetic energy, I use K. For potential energy, your textbook uses V, which I don't really like. I use P. And then for work, your textbook uses U, I use W. So please pay attention the difference between how I use notations and how your textbook does use notation. I absolutely do not like the notations of your textbook. I mean, T has nothing to do with kinetic, V has nothing to do with potential, and U has nothing to do with work. We typically use the first letter of that quantity as like velocity, we say V, pressure, we say P. So I don't know why T should be used for kinetic energy, but that's how your textbook is acting. So I just wanted to clarify this so there is no confusion. And so this is the principle of work energy. Everything is the same. The last thing is power. Power, if you remember, was defined as dW over dt, which we showed in the chapter. The chapter was it? It was chapter 15. We showed that you can also write it as F dot V, right? But over there, V was only one single number for the whole particle. Here, when we say V, we have to know V of which point, because different points on rigid body, they have different velocities. Which point? Well, it is the point at which this force F is applied, okay? So power is the force dot the velocity at the point where force F is applied. And this is if there is a force applied, that's how you define power. Sometimes instead of a force applied to the rigid body, there is a what? There is a moment or a couple applied to the rigid body, M. And the rigid body rotates with angular velocity omega, then you can similarly show that power is equal to what? M times omega. And the proof for this is by no means hard. All you need to do is to go back to this definition of work when it is a moment, right? You clearly see here work is defined as integral of m dt when you have a couple. So from here, if you see, clearly dw is m d theta, and then p, which is dw over dt, is going to be m d theta over dt, which is going to be what? M times omega, okay? So for a rotary system, the moment times omega is power. In general, power is always the product of a what? An inertia term and a velocity term, okay? So let me make sure that I add some good slides for you, some good pictures for you here that you can always refer to. So this is one big thing that I mentioned. The other thing, table that I would like to create for you is if you have a rotary system versus a translation. So if your system shows a rotation versus translation, how you define different things. Okay, so here, if it's position, if it's velocity, if it's acceleration, if it's work, if it's power, and of course you can add inertia, right? So then let me add a little bit more, maybe 2 more lines. So this is going to be kinetic energy. And this is going to be power. So what's the difference? Between a translation system and a translatory system and a rotary system. So here we go with theta, omega, alpha, I, integral of m d theta, 1/2 I omega squared, and then m omega. While here we go with R, we go with V, we go with A, we go with M, we go with integral of force dr, and then we go with 1/2 mv squared, and we go with F dot V. The other thing I can add for you is the cause of motion. Where the cause of motion here is a moment, while here the cause of motion is what? A force. So this side-by-side comparison hopefully gives you enough of comparison capabilities. So you can always have these two guys side by side, and so you can always compare. Okay, so these two would be some good slides for your course. Good, so we have defined everything. Then P average is still the same definition. It is the work divided by the time. Now, before I start solving problems here, there are 2 problems in this lecture that we need to focus on. One of them is example 19.3, which is a detailed problem, so I'm going to leave this for inside the classroom, and then example 19.1, which I want to solve right here. But before that, as I said, I want to focus a little bit, very small, on this formula and go back to the gear train. Okay, so if you have a gear train, and if you remember, when we have two gears, if this is the moment or torque in, this is the moment out or torque out, this is the omega in, and this is the omega out. And this is radius in, and this is radius out. If you remember, in the past we defined the speed ratio to be omega in over omega out, and it was equal to what? Radius out over radius in, correct? So this was the speed ratio. Then I also defined for you something back there, and I said I'll talk about it later, and that was called mechanical advantage, right? So this guy was the speed ratio for a set of mesh gears, and this guy is called the mechanical advantage. So it is defined as the moment or torque that you get in the output divided by the moment you get in the input, okay? And then, I guess again I drew it too big. Let me first make it a little smaller. There we go. And, oh no. Should do it again. Please bear up with me 1 second. Good. Please resize it. There we go. Now, if you remember, we also have some power in, and we have what? Some power out, right? So power in and then power out. Now, if we assume or neglect, if we neglect the energy loss inside a gear train or a gearbox, or say it's small, then we can say that power in is equal to power out. No energy is wasted. Therefore, according to this formula, power is what? Moment times omega. So it's going to be moment in or torque in times omega in is the same as moment out or torque out times what? Omega out. And from here, what is going to be moment out over moment in? Yes, you clearly see it is going to be equal to what? Omega in over omega out, right? So this equality here comes from this definition. And omega in over omega out is also equal to what? To radius out over radius in, and clearly it is the same as what? Speed ratio. So clearly you see that when back there I wrote for you that the speed ratio and the mechanical advantage are the same thing, there is a proof behind it. Okay, and here you can see the proof. Okay, so mechanical advantage and speed ratio both in a gear train are equal to the radius out over the radius in. So just wanted to tell you that. And clearly that's what I mentioned when you put the car, a manual car, in low gear. Low gear means big radius, output compared to input. So when you put it in low gear, it's kind of like opposite of this. The small one is the input, the bigger one is the output. That makes this speed ratio to be bigger than 1, therefore mechanical advantage is bigger than 1, so omega out is less than omega in, but M out is bigger than M in. So RPM goes down, torque goes up, and that's what you need in low gear. Opposite of that, you put it in high gear, RPM goes up, torque goes down. So you cannot increase torque and RPM at the same time, okay, inside the gearbox, because gearbox is a passive element. It cannot inject energy here. If it does anything, it wastes a little bit of energy due to lubrication, frictions, and some other things. So typically, P out is a little bit less than P in. It depends on the efficiency of the gearbox. But this is like an ideal case. Okay, so now that we have seen all the derivations and everything that we need to handle rigid body kinetics using work energy, let's now use it in this problem and see how we can employ these formulas. Okay, so in example 19.1, you have a circular disc with radius cap r, mass m, released from rest on the inclined surface with angle beta. And then assume that no slipping occurs, so there is rolling without slipping. The moment of inertia of the disk about the center is 1/2 mr squared. If no slipping occurs, determine the velocity of the center of mass if it has moved a distance of b units downward. So it is going to be solved completely parametrically, and we have to find velocity, and pay attention that there is no mention of time. Nobody cares about time, therefore the work energy method is a good solution method. Okay, so let's get started on this problem. So let's take a snapshot. And go to OneNote. So first, let's write down what we know and what we don't. So initially you start from speed of 0. So V1 is equal to 0 meters per second. And also omega 1 is equal to 0 radians per second because you start from rest. This guy goes down b units. What you want to find out is V2 and no slipping. That's the most important thing here, right? And I about the center is 1/2 mr squared, so we know that. Again, you see no mention of time. The distance traveled is given, velocities. So then we have to, of course, draw a free body diagram of this disk, which if we draw it, so I draw it here. The forces acting on it are mg. The normal force, this angle is beta, and then there is friction upward, which allows this object to rotate, right? Why is it upward? Because if you let it go, then the whole object, including the contact points, want to slide down, therefore the friction is upward. And then that friction about this center point creates a clockwise moment, which allows this guy to roll clockwise down the slope. Okay, so that is free body diagram. Then we need coordinate system, and I use the tilted version. So x parallel to the frame, inclined surface, y perpendicular, and then z out of the board. Okay, so now we are all good and set. It's time to write down the work energy principle, which says sum of the work done by all forces, which in this case it is W12 of mg plus W12 of n plus W12 of f. This is equal to kinetic energy in situation 2, which is 1/2 mv at the centroid squared. Of course, v at position 2 of the centroid squared plus 1/2 I about the centroid omega squared, and then minus initial kinetic energy, which is the very same thing here. If you want, I can write the whole thing for you, but that's basically this guy. Except instead of position 2, it is in position 1. Okay, so this is the principle of work energy, and maybe I wrote this too big. So, but that's okay. We know that initial kinetic energy above 0, so nothing here. In second position, omega is unknown, v is unknown. Now let's focus on the work done by these forces. Clearly, work of n is 0. First, if you notice, n and friction are both applied to this point A, and gravity is applied to this point C, right, the centroid. So n and f, again, these two are applied to point A. And what is the velocity of point A? A is the contact point, and here you have what? No slipping. No slipping means what? Means velocity of point A is equal to what? 0. And when you apply a force to a point that does not move, so you know work happens when there is a force and there is a displacement. When there is no displacement, even for that moment, there is no work. Another way to look at it, you remember power was what? Power was force times velocity. When velocity is 0, power is 0, therefore there is no work. So none of these two guys is doing anything because they are applied to stationary points at that point, at that moment. Work of mg, there is a formula for it. It is negative mg delta y of point C. That's all it is. Okay? So what is delta y of C? Now here is the dangerous part. If you compare this y against that y, you can be in trouble. Because along this y perpendicular to the surface, inclined surface, there is no displacement. So you might be tempted to say this is 0, but it's not. So what I recommend you do instead, I won't call this x, y, z, I would call them x prime, y prime, z prime. And then I also have my conventional x, y, z. So, and even I can just not use this this guy here because I don't really need it. So I can use this one in this case. So when I refer to y, pay attention, whenever I refer to y in the formula for work of gravity, y should always be upward, downward. So it is this y. And you know, when you go down a distance of b with angle beta, you are forming a what? You are forming a triangle, and the amount of vertical displacement is b times sine beta, and since you go down, that's negative. So this guy is negative b times sine beta. So now, if you look at the two sides of this equation, so this is all zero, good. So I have one equation with two unknowns, VCM2 and omega2. And you know, you cannot solve one equation with two unknowns, but since the kinetics is dead end, we go back to kinematics. This guy is rolling without slipping, so there is a relation between V of the centroid and omega, right? So rolling without slipping means two things here. First, the contact point velocity is zero. Second, you know, velocity of the centroid at any point is what? R times omega. That's the condition for rolling without slipping. Therefore, I can say that since my unknown here is V, for omega, I'm going to replace it with what? V of Cm in position 2 divided by R. And so now I only have one unknown, V of Cm2. Okay, so I replace it with that. And there is one unknown, and if you solve for that one single unknown, you're going to see that V of the centroid in position 2, it is going to be square root 4GB times sine beta divided by 3. There we go. Problem solved. Okay, so that's how we solve this problem. Now, what if we wanted to solve this problem using the second law of Newton, right? And we did not want to resort to work energy. So we wanted to go to that planar equations of motion we had in the previous chapter, and we wanted to solve this. I'm going to do it for you here, just so that you can compare this solution against that one and tell me which one is easier. So what I would do is I'm going to copy and paste this whole thing here, which is basically the FBD, the coordinate system, and everything. So let's go here and paste it. There we go. This time I'm gonna do it with the work energy, the second law of Newton. And since here I don't have to have y to be vertical upward, so I am going to call this x prime, y prime, z prime, and not xy, xyz, not the primes, because I don't need the conventional y. So here I have three equations for motion. Some forces in the x direction, which is negative f, and then plus mg sine beta, right? You know mg has two components, one here and one here. This guy is mg sine beta, and this guy is mg cosine beta. So mg sine beta minus f is equal to mass of the object times acceleration of the centroid in the x direction. Sum of the force in the y is equal to n minus mg cosine beta. This is equal to mass acceleration of the centroid in the y direction, and some moment about the centroid, counterclockwise positive, which is equal to clearly negative f times r, right? Because The only force creating moment about centroid is F, and it is clockwise, and this distance is R. So negative FR is equal to 1/2 I about the centroid times omega times, I'm sorry, there is no 1/2. That's kinetic energy. It's I about the centroid times alpha. Okay? So now, how many of these you don't know? One is F, the other one is N, ACX, ACY, and alpha. There are 5 unknowns, and you know you cannot solve from 3 equations, but from kinematics, you should be able to take care of ACX and ACY. First of all, ACY is clearly 0, as this object is not going to get off the surface. And ACX, you know, because it's rolling without slipping, V of C is R omega. If you take a time derivative, you remember that acceleration of the centroid, which is here in the x direction, of course, is R times alpha, right? And so if I want, I replace alpha because I need A. So alpha is AC in the x direction divided by R. So I replace it here. Equation number 2 is not going to go anywhere because it only gives me N, and I don't like N. I don't care about N because this friction, that's very important. Let's talk about this. This friction here does not have anything to do with N. This is a static friction, and for a static friction, there is no formula. So you might say, then what was that mu s times N? Remember that mu s times N is only for what? To give you the maximum friction capacity of the surface. It doesn't mean it is happening. That mu s times N happens only when you know that your object is about to slip. Here there is no such a thing as whether it's about to slip or not. So remember, again, there is no formula for and this is a static friction, because this point does not slip. So it's not also equal to mu k times N. That is one of the most important things about this problem. If there is no formula, you have to find it from these formulas. Clearly you see, for example, F is IC alpha divided by R. So this static friction comes and calculated from dynamics or statics equations. It is not equal to mu s times N or equal to mu k times N. So let me write it for you. This is not equal to mu s times N. This is not equal to mu k times N. Okay, don't be tempted to do so. That's a big mistake. So now I have this equation number 1 and I have equation number 2, and since I don't care about F, I eliminate F between 1 and 2. How? I multiply 1 by R so that I get the negative FR, and then I subtract. So I multiply R to equation 1 and then subtract the result from 2. Therefore, both here and here I have negative FR. When I subtract, that's going to go away. So if I do that, on the left-hand side, I would have mg r sine beta, correct? That's all. And on this side, I have ACX times mr minus IC over R. Now, what is IC itself? The problem is telling you it's 1/2 mr squared. Okay, so it is going to be minus IC over R, but IC has R already, so 1 R would cancel, so you're going to get negative 1/2 mr. Which, by the way, these two, when you simplify it, is going to be negative 1/2 mr, positive 1/2 mr. And from here, if you cancel M and R from both sides, you see that ACX is equal to 2G sine beta, which I guess we solved for this in one of our previous examples. Okay, so this is the acceleration of the centroid, 2G sine beta. And now, look, Initially, the centroid has a velocity of 0. Finally, I don't know. And the distance it travels in this direction is b units. And by the way, you clearly see that the acceleration that the centroid has in that x direction is a constant number, right? This is constant. So when you have initial velocity, you have a constant acceleration, you know the distance traveled, and you want final velocity. Which formula do you use from kinematics? You are right. Can I use the time-independent equation, which says v of c2 squared minus v of c1 squared is equal to 2 ac in the x directions times delta s, where this delta s is b, this guy is 2g sine beta, this guy is 0, and if you calculate, you will get something, I guess, similar. I'm just missing a 3 somewhere here. Okay, just missing a 3, and I have to make sure where that 3 comes into play. So that equation is correct. This one is correct. 1/2 mr squared. All look correct to me. And I multiplied and subtracted MRA, and then -1/2, so it's -1/2 m and r simplified, 2g sine beta, this, yes. So I don't see a c here, a 3 here, I'm sorry. Okay, yeah, I delved more and I found where we went wrong. That is a very subtle thing, but we have to really pay attention. That all goes back to the directions. Okay, so let's talk about this. So that's all about this equation that we used. So here, let's see. Your alpha is in this direction, right? And your AC of x is in this direction. Now, the problem is this. This A is in the positive x direction, but your alpha is clockwise. So this formula is correct only if the magnitudes are considered. But when the sign comes into play, because you know everything here has a sign, when the sign comes into play, this alpha, which is clockwise, is what? Negative, right? While ACX, which is in the positive x direction, is what? Positive. So when you look at this equation, it cannot be if we are observing the sign, because R is always positive and alpha is negative and ACX is positive. It cannot be, right? Product of positive negative should be negative, not positive. So this cannot be unless, since alpha is negative, to make the equality hold, I have to do something. I have to add a negative here. Let me use a different color and make it bold so that you see it. Okay, I have to add that negative to make it happen. And therefore here there is also this negative. And therefore here there is this negative. And so here this is going to be positive. And so this is not going to be 1 over 3, it is going to be 1 over 2, it is going to be 3 over 2. And so this is going to be 2g over 3. Okay, so 2g sine, and let me make sure I'm not making any other mistake, because that could be quite bad. Okay, you have to make sure you make the smallest mistake, and there we go. You get a completely wrong thing. So if I look here, I have to divide by r, and this is mr, this is 1/2 mr, that is right, and I multiplied both sides of that and didn't cancel this. Yeah, that is all right. Therefore, if I calculate, so I cancel m, I cancel r, 2g sine beta over 3. So there is a 3 involved. Okay. So there is a 3 involved. Still constant. And here I have this over 3, right? And therefore, if I calculate now VC2, it is going to be the square root of the right-hand side, which is 4g sine beta times b divided by 3. Which is exactly this one. So I got the same answer I got with work energy, but it involves more solution, right? One of the equations definitely didn't work. The other two I have to simplify. I have to also use kinematics, which I use in the other case too. I use kinematics. I use this relation, but this one, not the other one. And then I solve. So you can see the work energy can provide the solution in a much faster way. And the only reason here is nobody cared about time.